It's
whichever's easiest for you. I mean, I may as well be standing up, I guess. So it's a bit of moving around once we get going, doesn't it? We can do it. I don't know. If you, get started. It'll be Matt will start. Sit down. No, we're happy.
So I'm bringing the people here.
And we'll start on time, or should we wait for? All right, but we'll start. We'll give it to you. All right. Okay, but we don't. Okay. Oh, yeah. Okay, can we take seats, please?
I'll pass it over to you. We'll just sit there.
I'm very good at it. I can just very naturally. You know, talking like Donald Trump. But I can Google that. I can get you.
by industry representatives from Airbus, Jose Sanchez Gomez, from Safran Aircraft Engines, Jan Marshall, and from Rolls-Royce, Neil Mantle. Okay. The purpose of this panel is using some current themes in the areas of composites and additive manufacturing to explore both from an industry and from an agency perspective as to what are the challenges and opportunities for us as we move forward with some of these technologies. So, I would ask my colleague Simon if you could introduce the subject.
Hello, I'm Simon Waite, and as Matt said, the theme is digitisation or the advance of new technologies. And I'm going to start with one of my interest areas, which is composites. Introduction of new technologies is nothing new. And we've currently been, I have it on the slide here, we've been established for 40 years with composites in large airframes. The issue is the rate of change and the application of change. So on the graph that you have there, you see 40 years. We had the ATR wing box in the 80s, and the big step change has been the sudden change to extensive fuselage composite structure. We now have, that has been a shock change in terms of many people have suddenly been exposed to composites for the first time en masse. But this is quite, as I acknowledge quite readily, we've had critical applications in small airframe, propellers, rotorcraft for a very, very long time. So we've had it's been a slow ride up to this last step. And we have a population of people who know something about the subject. And the acceleration has changed how we manage data, how we manage people. And the current technology that we're talking about a lot now is additive manufacturing. So what's happening with this? Can we learn lessons from the past? How quickly will this technology come in? Will it be an extensive percentage of the airframe very quickly? What's the criticality? We already know, well, from the start, we already have some serious applications like fuel nozzles out there certified. And the question is, how do we manage all this? So trying to catch key themes that we are finding in the material world, we've got to remember that material and process defines the engineering properties that we work with. And as we have more integrated new methods, we're forced into defining materials and engineering properties at a higher level in the test and analysis pyramid. And this can be quite a challenge in terms of understanding the material. We have the increased use of or move towards process control rather than inspection control. This is happening quite rapidly. We also have to think about understanding at a statistically credible level the new damage modes. At the same time, in terms of the business model, we have globalization happening. And this has resulted in extensive subcontract dispersal within and between production, design, and maintenance. So this adds a whole series of challenges in terms of the difference between moving data sets that are digitally based to the physical reality of these items existing somewhere in America or in Europe. Further to that, we have compressed timescales, and we've seen a number of large manufacturers suffer from overstretching themselves and overstretching their resources and their reach with subcontract control, and the belief that the ability to move information digitally constitutes an equivalence to operating with a core activity in one location. And if you look at the integrated activity that we are thinking about with some of these new technologies, there's a divergence there between the global business model and the technical model to some extent. And we've got to think about knowledge base and training. So with that, I hand back.
Thank you, Simon, for the introduction. So the plan for the rest of the panel is that we'll hear from each of our industry panelists in turn with opportunity for a couple of questions in between. And then we will wrap up with EASA's position and how EASA is trying to work with industry in enabling some of these technologies. So could I pass mantle over to you then, Jose?
Hello, good afternoon to all of you. I'm Simon. Many thanks for the kind invitation to be panel member. I will start with a short introduction about Arbas. I think all of you know perfectly what is Arbas. We have 4 families of product, but the today presentation will be mainly related with the family of the 350. Why? Obviously, because the title of the presentation is Composite Material, and 350 is a good example of application of composite material. Just starting with the history in our company about composite material. This morning, Jeffrey, you speak about several times about innovation, and you mentioned composite material, and in my opinion, this is true. Introduction of composite material in Arbas has been started 40 years ago, as Simon indicated some minutes ago. We start with very simple parts, with glass epoxy laminates, some with a structure, but step by step, we introduce many structure and many material, and this is due to a big effort in innovation and also good collaboration with authorities, including EASA, and I think it's the best way to improve our product and to introduce new material and new structure in our aircraft. I think our history is an history of a step-by-step introduction of new material and technology. First 300, later on 320, where it's a very good example of new technologies introduction. Big effort in order to introduce new part with composite material, starting with BTP, HTP, movables, etc. And step by step, we increase the number of composite material and structure in our aircraft. And maybe the next real step is 380, where the quantity of material is huge. We have many tons of composite material in this aircraft. But finally, 350, where more than 50% of the structure is composite material. And in this area, it's not only a quantity of material, it's also what material we are dealing. And again, it's an history of investment in development, introducing new material. And when I am speaking about new material, I am thinking in new fiber. Today, we introduce intermediate modulus fiber, but also new material formulation, and especially new architecture of the material. And the last point is key, because every time that we are introducing new material or new technologies, obviously we have new problems that we have to manage, and the best way to manage is to have a proper collaboration with our supplier and with our aeronautical authorities. In this area of the supplier innovation, we have several contracts in Arbas where we are working with the more relevant companies around the world in order to develop material, especially for us, for Arbas. But this presentation is related mainly with 350, and I have selected 2 parts. One is the wing cover. That is, we are in the company especially proud about this innovation. The first one is the wing cover. It's a huge part, 32 meters long, and in this case, it's a co-bonded structure. So this means that we make a huge effort. We are using a lot of material, and the technology developed to produce this part, plus the complexity of the process is very high. And as a consequence, at the beginning, we introduce a lot of control in order to handle the proper quality of the part. Okay, that later on we will discuss. This is an example how we are producing the part. As you can see, first we cure the skin. Later on, we produce the stringer. We produce a co-bonded structure. And later on, finally, we produce the process control specimen, the NDT, plus the dimensional and visual inspection. Today, our company is proud that never is enough. We are always trying to improve our technology. Never is, our today technology is good, it's very safe, it's perfect, but we can make something more. And something more today is related with what we can do to reduce the scrap material. The price of the material, the composite material, as you can imagine, is very high. So if we are buying material that at the end we are scrapping, it's not a very good business. So it's why we are developing new technologies in order to reduce dramatically the scrap ratio of our material, because I think it's our obligation, and second, we are working in the society, and as a consequence, it's not fair to produce a lot of scrap. And second, obviously, we want to increase our productivity, improving, if possible, the performance of the part. This is the today example, what we are doing in the wing. Okay, so we are changing the technologies for ATL technology to FLU technology, with the main target to reduce scrap and also to improve productivity. Okay. What related with this manufacturing process, and this is important for the final conclusion, every time that we are making a change in the process, we are making two items. First, we are making a robust development, and in this robust development, we are making a process that is called first part qualification. I will come back later on to this presentation. And first part qualification for us is very simple. Every time that we produce a new part, we are cutting the complete part in small pieces in order to check what is the internal quality of the part with microscopic inspection. We are checking the manufacture, we are checking the mechanical properties of the part, and we are making a correlation with non-destructive technology. And related with your presentation, Simon, about globalization, this includes every time that we change our supplier. So imagine that we are changing the supplier of the aileron from Europe to USA or from Malaysia. We check case by case if it's necessary to perform an FPQ. FPQ is not a cheap process. As you can imagine, to cut a wing 32 meters long is a very complex process. We produce thousands of specimens, but at the end we have a clear concept of quality and what is the real part that we are producing. We have a good correlation, and is the basis in order to later on reduce or to rationalize the quality control that we are making in our parts. The last part is related with our certification pyramid. I think all of you know perfectly our certification pyramid. But a part of the typical testing, also we are making something that is relevant for the future of our quality control, is we are considering at several levels of the certification pyramid defectology and possible defect that we can create, or during manufacturing, during transport, during installation of the part, or even during service of the aircraft. Okay? So all defectology has been considered during certification pyramid, starting at very low level, at coupon level, and later on, step by step, we increase this defectology, finishing in the real test, in the final test of the element, where we introduce different type of defectology in order to cover possibilities that we will have, again, as I indicate, during production, transport, installation, and even service of the aircraft. The second part that we are really very proud. Does not mean that they are only one. They are producing very impressive part in Airbus. I think some of our competitors that are here in this meeting also produce very, very relevant and very interesting part. Is the Section 19 fuselage. Section 19 fuselage is a co-cure process, a totally co-cure process that is very innovative in the industry. As a consequence, very complex tooling, very complex process, but it's a full barrel part, maybe the more relevant produced in Europe. And in this case, it's a pure co-cure process. And as a consequence, we are making a huge effort in order to make a proper quality control from the beginning, including process control specimen, visual, and also NDT inspection. This is a photo of this part. It's an Omega stringer part, fully co-cure, no adhesive between the Omegas and the skin. And as again, it's a full barrel that we are absolutely proud of this part. Okay? And just as a conclusion, our intention in the future obviously is to rationalize our quality control that we are making in the part. Today we have a huge experience that we have during the last 40 years related with this quality control. Obviously, this quality control has to start from the beginning, from the design of the part, during manufacturing and concept of the part, during manufacturing, engineering, development. Every time that we are making a development, we need a real process in order to make a robust way of making the part. And finally, this is the only way, in our opinion, to reduce or even eliminate some process control specimen that we are running today, to rationalize the visual and dimensional inspection. And we are working today in the area of non-destructive testing in order to really try to make a better use of this technology that are very expensive, obviously necessary, but we have room for improvement and for reduction in the future. Okay, thank you.
Thank you. Thank you, Jose.
And Jose, one of the key things that's going on at the moment is the evolution of the materials and the move towards process control and digitized control from moving from inspection. Is this something that's happening as an active policy within Airbus, or is that something that's drifting in as the opportunities arise?
No, it's an active policy. We have an active policy first to reduce to develop new material. And one of the part of the new development in material is obviously we are making more robust material in terms of tolerances. It's a key for us. We are proud with some of our suppliers. We have reduced dramatically the tolerances of the material in terms of thickness, in terms of width of the fiber placement of ATL tapes. And this is part of the better quality control. we have experienced in many parts that during many parts produced, we have zero defect. And obviously, as a consequence, we have an active policy in order to rationalize or even reduce, and even maybe why not to eliminate some quality control that we are making today.
Yes, and that has you have a standardized equivalence process in terms of the use of the pyramid relating to the switch between inspection and process control.
Absolutely, yes.
Yeah.
Yes.
Okay, thank you.
Thank you very much, Jose. So, moving on to our next panelist, if I could ask Jan to take the floor. Thank you very much.
Good afternoon. So my presentation is on the LIP composite fan blade. So I'll start first with a general description of the fan blade technology. So you can see here on the picture what does the engine look like with its fan blade on the front. Sorry. Yes. So the composite fan blade technology developed by Safran for the LIP engine is based on a 3D woven architecture of carbon fibers. So this is based on a specific pattern that has been designed specifically for damage tolerance. And this specific pattern is implemented into a weaving program that's loaded on a weaving loom. And the resulting fabric from the loom is then positioned into an injection mold that is finally injected to end up with a injected fan blade that's then finished with leading edge bonding and paint. So we are using composite, obviously, for the weight savings that the material can offer, and then the performance improvements. Going a little bit deeper into the manufacturing, this slide shows one specific item to our production. That's everything that's going into our plant is only raw material. We have only fiber on one side, resin on the other, and all the manufacturing process that's after that is fully controlled within the plant. So the fiber architecture manufacturing, the fiber placement into the mold, as well as all the resin introduction. A little bit of history now. It took a long time to develop this new technology for us. It's been over 10 years of development prior to start the certification process. We started first with a whole technology screening to make sure we could identify what is the best and more robust possible technology for the LIP fan blade, and then started with the large engine scale to end up downscale the parts to the LIP scale, which is much smaller. During all those years, we also started very early discussion with EASA in order to prepare the certification path jointly, and to make sure we would share our development of the technology, our understanding of the material behavior, as well as preparing some specific certification conditions. One example for the joint work that has been performed with EASA is the special condition for the fan blade. Basically, when you want to certify an engine, you need to demonstrate by testing that the engine can sustain the load of a fan blade loss during the engine rotation. Usually, this test is performed by releasing a full blade and introducing the weaving, the carbon weaving technology. We wanted to use the enhanced damage tolerance and fatigue properties of the parts in order to release only the flow pass area and demonstrate the same level of safety for the engine. This ended up being the special condition that's been dedicated to demonstrate that same level of safety by releasing on one side only the flow pass of the part, but also demonstrating the level of robustness of the green area in the picture here by demonstrating that it can sustain 2 times the maximum load that is being seen on the engine, and also demonstrating cyclic life above 100,000 cycles. There are also other aspects of that, like lightning strikes, or also fleet leader programs, and robustness towards damages in service, for example. The second part of the presentation is about how we integrated the process into our designs for the lip part. This slide here is showing in blue the typical design loop for a fan blade, going from a 3D design of the part and then calculating the mechanical behavior of the part to have the shape of the parts at all engine speeds. That allows to calculate the aerodynamic performance of the part at all those engine speeds. And ultimately, we can also perform some fast functions calculations to predict the behavior of the part under some specific events like burst strikes. What we introduced specifically for the carbon fiber composite blade is a process simulation within that loop. That's introducing weaving simulation as well as forming simulation for specific reasons. The first one is that we could determine as soon as design is done if the part is feasible, but also those simulations are there to provide some input data for the mechanical simulations. So we could make sure that we calculate a part that will be manufactured. Once the design is satisfying, we can also directly use those specific calculations in order to feed the manufacturing programs and parameters in order to have a full adequation between the part that has been calculated and the part that is being manufactured. Ultimately, this part obviously is tested in order to make sure that the expected results are correctly in the part. This slide here is an example of the kind of tests, subcomponent tests that we performed in order to optimize the weave pattern. Those are small videos of impact testing that we performed on some panels that have the shape of the tip of a fan blade. They have the exact same geometry, and they were impacted with the exact same energy. And if you look on the left one, you'll see that it breaks directly under impact. And if you look at the right one, it doesn't break. The only difference between those two panels is the weaving architecture inside them. So we used extensively those kinds of subcomponent tests in order to verify that the technology we were developing was in the good direction and the most robust possible. Another item here is that we spent many campaigns of testing in order to understand deeply the damage scenario of the material and to end up with design values that are robust enough in order to sustain all the life constraints of the part. For example, the 100,000 cyclic life that I spoke about previously. So all these fundamental knowledge of the material was very important in order to bring enough confidence in the part that we were designing, and also to manufacture the most robust possible part. Many systems were developed in order to have a full knowledge of this material as specific acoustic emissions in order to identify all the level of the first damages on the composite material, for example. Finally, how did we validate the whole technology? We did the same way my predecessor did, presented, using the building block approach. So that's the pyramid of all elements that making sense together. You can see on the bottom all the material testing, material understanding, fundamental understanding of the material behavior, going up to the design and the subcomponent test, full blade test, as well as parts behavior within the engine, and that ultimately the manufacturing controls that are there to make sure that every single part that is being produced in the plant is the exact same replica as the part that was tested during certification with success. During all those steps, we also introduced some manufacturing anomalies, intentional manufacturing anomalies, as well as intentional in-service damages, in order to check the robustness and demonstrate the robustness of the parts towards those kind of situations. Finally, what we learned through all those developments can be, we try to summarize it here in 5 points. The first one is that starting from the identification of the structural need for the parts to identify what is the best technology available is one major item for the composite industry. Then working on the development on the structure at the same time that we are working on the development of the manufacturing process is also a key point. Identifying failure modes to have a fundamental understanding of the material behavior and performing subcomponent tests is key. Developing specific calculation model, finite element analysis models to predict the behavior of the parts, and also process simulations in order to make sure we have a full adequation between part design and part manufacturing. And at the end, of course, one key point that helped us a lot, for example, with a special condition, is to engage very early discussions with the regulation agencies in order to share the development and share what we are optimizing in order to make sure we have a optimized process when it comes to the finalization of the certification.
Thank you, Jan.
So, Jan, in terms of moving digital packages around and refining and stabilizing process, what lessons have you learned? I mean, have you, between the management of digital data and the physical management of the part, and correlating the two in terms of the execution of the use of the pyramid?
Yes, so there are some challenges, of course, with all the digitalization of the production. We use the digitalization for many items. I presented the process simulation in order to have this kind of robust adequation there. We are using, of course, digitalization for production management, as well as we specific developments that we did for digitalization of the NDT that are performed on the parts. So there are many challenges there, sometimes that are facing some physical limitation, of course, with the when it takes to some anomalies that can occur in the parts. Digital simulations doesn't do anything, and if there are some physical limitations on the parts, that we need to test them physically in order to assess the compliance of the part.
So those changes or the lessons you've learned have fundamentally changed some of your strategies in terms of production choice as well. That's what I understand, and that's what you're describing. Yeah.
Yes, yes. We try to anticipate the most possible through simulation, the manufacturing trends and that kind of thing, in order to be the most efficient possible.
Okay.
One last point, Jan. Something which is clearly very, very relevant and of great interest to our audience at the moment is with the expansion in the drone industry. You've talked about damage modes, etc., and exposure to damage. What are your thoughts going forward on the potential considerations of drone, etc., and whether that poses a new threat to aircraft and engines? Do you have any thoughts on that and how that may evolve?
That's a specific domain. What's trying to understand, as you said, the fundamentals of the failure modes and the tolerance to damages is, of course, a key element in order to make sure that the technology that can be chosen for any application is the most relevant one. given of the structural needs of those kind of aircraft, for example. What is the best choice to perform? It has to be correctly chosen based on the knowledge and the potential of different technologies, yes.
Thank you. So, Neil, could I ask you to talk to us about additive manufacturing? Thank you.
Good afternoon, everybody. My name is Neil Mantle, and I head up additive manufacturing for Rolls-Royce PLC. Obviously, we are a large engine manufacturer, and additive is a rather disruptive technology that lends itself to extremely complex and challenging components. And the picture as a backdrop there is the front bearing housing of our XWB 97,000 pounds thrust engine. It's a development structure which we use to certify the ground running and the flying testbed application for the engine, and I'll take you through some of the steps that we took, and equally why additive is a challenging but rewarding subject. So from this slide, and we heard this morning from Jam, actually manufacturing is changing. We've got specialist providers, we've got the circular economy, we've got the way that actually we're looking to streamline value and bring value both in home and at the wider marketplace, and the pace of change is extensive. So agility in manufacturing is certainly something that is really, really important to us, both in design, in manufacturing, and in the circular economy and the repair of components and the longevity of the fleet. That leads us to agile reconfigurable manufacturing, and some of the drivers of that are intelligent manufacturing. We've all heard around Industry 4.0 and the activities that digital takes in that space. We've got disruptive processes, which is where additive manufacturing comes in, and I'll talk a little bit more about that in a minute. Digital data and systems connectivity. We heard from our colleagues just previously about how they've used digital transformation and digital simulation and digital twins to simulate and develop capability in the digital world, and that leads to different levels of collaboration and also levels of training and understanding. So, what is additive manufacturing? So, those of you in the room will have heard of 3D printing. Additive manufacturing is a 3D printing method where we actually create component forms and surfaces by building up layers. But because additive manufacturing or 3D printing is so broad, I'm going to talk a little bit about metallics. Obviously, the engine is full of metallics, and some of those metallics are really quite challenging. And even in that space, additive manufacturing is split into a multitude of different methods. Direct energy deposition, where we can take very, very large components in metallics, which might be produced by metal wire, which is larger scale. Metal powder, blended powder deposition with laser sources, which lead themselves to freeform component manufacture and also then repair of components. And there will be people in the room today that's also familiar with that, and high integrity repair. And then powder bed fusion, where laser and electron beam methods are used to actually physically selectively melt metallic powder that's laid down to grow the component from the bed all the way to the top. So complex subject, and different processes and different methods lead themselves to different applications. So what are the key benefits? Well, the opportunity to make highly complex shapes in difficult and expensive materials is very, very rewarding. It's toolingless. It means that we can be fastly iterating, and we can use it not only from rapid prototyping, but also now through to component evaluation and production. And you can create unique functionality in components that you can't create by conventional means. So that really does open up the design space for you and allows you to provide functionality, whether it's weight, performance, emissions, into the component that you can't get by other means. So that gives you a real opportunity to optimize your components and optimize your product. It's fast with less waste. We heard talk about how use of materials and the environment is really, really important to us. You only selectively melt the material that you need to, the other material you don't, and then you recycle it. And it reduces the number of processes, and then actually you can start to combine components together into assemblies that were previously fabricated or bolted together as individual components. And this, as a principle, really changes the process change and provides some quite unique business opportunities. So, as a company, you would expect that we insist on comprehensive demonstration, whether it's from a target product level, whole engine demo, core integration vehicles, component level, and then subcomponent level. And additive manufacturing is absolutely no different. There's no magic opportunity here to forego this definition and rigorous testing. The pyramid model that our colleagues have just talked about is exactly the same. Additive just gives you the opportunity to speed up that process. But your integrity is really, really important. So, what's our approach? Well, in order for us to get our arms around this exciting technology, we established the Centre of Competence, which is what I lead. That is a centre where our specialists, who are specialists in additive layer manufacturing, are all housed, and we're able to focus on alloys and components across our product area. Integrity, product integrity, materials integrity, design integrity is absolutely paramount, and you'll hear me and see in a minute where I show how those are all intrinsically linked. And in order for us to understand what it means to use additive manufacturing, we need to be an intelligent user, definitely before we become an intelligent customer. That principle of understanding exactly what it means and what it takes to deploy and use additive manufacturing is absolutely paramount. So, it's what I've termed a license to operate. It brings together manufacturing, materials and design, consistency of fabrication methods, suitability and durability of the materials that we're depositing, which all builds itself into a material strength properties and design database, which enables you to deploy and take full use of this exciting technology. And really, that license to operate can only be achieved when you have all three disciplines in place. So you can't deposit material without understanding its material capability, and you then can't apply that in a product unless you understand what unique or different design characterization there are for that product. They all go absolutely hand in hand. So, that leads you to a stepping stone approach, and that stepping stone approach leads you to opportunities where you can substitute components, where you can provide what I've called smart enhanced substitution, where actually you can substitute for a component, but you can add value. That may be weight. You may be optimizing a geometry within that component, which means that you are not completely redesigning the whole engine or the whole product, but you are providing functional opportunities. And then, of course, one-way choice, which is where you are absolutely, totally and utterly using the technology to gain full value in the product that you are designing and manufacturing. And that maximum benefit from that is at the end, whereby you are absolutely harnessing the full ability to manufacture and design components that you can't make by conventional means. But that comes with a stepping stone approach, so you understand integrity and you absolutely understand what it means to manufacture components using additive layer manufacturing. And of course, we're actively developing products and applications in all three of these disciplines. So, an example of what it takes and what it means to do a large additive layer manufactured component. This is our front bearing housing for our XWB-97. It flew on the flying test bed, which was an Airbus A380, and we flew that late in 2015. There's a picture of the component. What you see on the left-hand side is the front bearing housing. One of the very normal questions I get was, did you 3D print the whole component? And the answer quite clearly to that is no, we didn't. But each of those titanium aerofoils, which you can see on the right-hand side, are all additively manufactured. There are 48 of those titanium aerofoils in every structure. Those components are in excess of 300 millimeters high. They're made out of titanium 6.4, and we've proven absolutely that they are equivalent to conventional manufactured components before we were even able to progress this forward. The structure normally are either cast as singles, what we call the ring of vanes, so that's the full annulus of the vanes. We also have cast and fabricated versions and forged and fabricated versions across different engine types. So subsequently we had a really strong baseline for which we could benchmark and optimize additive. So it's not a short process. The program for developing that component was around about 5 years in the undertaking, from initial technology samples all the way through to the first significant load bearing structure. Over 200 test data points before we even started manufacturing components, and then when you start to manufacture components, you've got sub-element tests and full element component testing to go on, and every time you're manufacturing components, you're gathering data and you are building your database, and you are holding your process to a very, very high level of scrutiny in order for you to develop the technology. Materials, manufacturing and design in full combination. So there she is. The blue element at the front of the engine is the front bearing housing. It takes the air from behind the fan into the main core of the engine, and it maintains and holds the annular front bearing of the main engine. It sits 1.5 meters in diameter. It contains 48 titanium printed aerofoils within it. In so doing, because we were able to iterate and we were able to use the technology to its advantage, we actually took 30% out of the development time for bringing the first front bearing housing to its first engine test. That enabled our engineers to work more conclusively and longer on the design, because we didn't have to release long lead patterns and castings for that large structure. It gave us the opportunity to take the pressure off that process, but also to optimize, ready for a far more flawless launch when we brought into operation for the production elements the full cast front bearing housing. So I think that's an example of additive where we've used it for speed, we've used it for equivalence, and you can see that the opportunities are pretty great with respect to using the technology. And subsequently, we produced hundreds of aerofoils to support the program, all made to exacting full fixed process control, and we've got tens of thousands of hours worth of manufacturing experience that backs that up to enable us to continue to develop this and other parts of that exciting technology. So thank you.
Thank you, Neil, if I may. You talked about the different metal technologies in the field of additive, and we see from different applicants using the electron beam technique or the laser process. Could you describe for us in a few simple words as to the pros and cons and where we can expect to see those different types of technology?
Yeah, certainly. The electron beam process enables you to deposit material quicker. It means you can create larger components faster than you do with a laser-based process. And because it's an elevated temperature process, the components are relatively residual stress-free as well. When you produce parts with laser, you have residual stress that's built into the components. Laser generally produces a finer level of detail, and subsequently, as you start to move into more finely and very acutely designed components, laser lends itself to that. And then when you think about repair, you would be using blown powder, which gives you that further control with the deposition of the materials as you start to repair other critical components.
So, taking that point, and a question that's come from the audience is that how does that lend it to post-processing techniques, heat treatment, etc., and where do we see a difference in, do we see different challenges that require different heat treatment, or does it exempt us from the need in certain post-processing techniques? What are your thoughts?
Certainly, post-processing is really important. I talked about laser with its residual stress, and so subsequently you've got stress relieving and potentially hot isostatic pressing. Defect control, abnormality control, and the way that you understand that in process is really important. And subsequently, that's no different than it is in certain casting processes. I think the importance is to really understand the material properties that you're depositing, to make sure that you ensure that you have got either equivalence or you understand that you've got a consistent difference, because you might start off with a consistent chemical specification, but the characterization of the material that you deposit could be different, and in certain cases it's very different. So in order to make sure that you can control that, you need a consistent approach, which does include post-processing, but that also then couples back with design.
Thank you very much, Neil. Can I ask you to start the discussion in terms of how the agency is trying to act as an enabler for technologies? Thank you.
Thank you, Matt. So we've seen some good examples there of rapid introduction of new technologies. And back to the regulator, thank you, back to the regulator, how do we plan to manage this? Well, if we look at the regulatory structure, we have a pretty robust structure, and it's being moved towards, we keep hearing about performance-based requirements, and that's definitely the direction it's heading in. If you want to look at those requirements in terms of materials and process, then it's covered at a very generic level. So at the top level, we have the basic regulation, and as you go down the pyramid, you go through the implementing rules, and we end up at these cert specifications and the guidance material. And these are non-binding. The implementing rule and the basic regulation are binding. So what guidance do we get regarding materials and their importance? Well, at the basic regulation, it says structure and materials, which is fine. It's telling us that materials are recognized. Structure is not much use to you if the materials aren't controlled. And the basic regulation says that you need to be good for the envelope of the application and for the duration of the life of any part or product. So we go into the implementing rule, design captures it, it now identifies material and process as key to this activity. And in fact, it's linked to type design. Good materials are linked to type design, that's understood. If we go down to the certification specifications and the lower level non-binding guidance, we have clear direction in terms of 603, which points at the need to deal with durability, the environment, and you need to show that your materials are good for that application. We have 613, which needs to be statistically credible. One of the things you've heard about is the identification and management of the correct damage modes. That is essential to transferable production activity in a global sense. And if we look in production, the guidance material, we have production requiring the management of change. So it's a fairly robust framework, fairly generic, and quite useful for our needs now. One particular requirement is 605, which we've been using rather a lot recently, and it comes back to that pyramid. I keep pushing on the pyramid and the separation between confusing data sets with the product. This, for example, we've had a good emphasis from the examples that were presented on the need to use and find an equivalence and use that test and analysis pyramid appropriately. And this has serious implications for the repair world, and we've been trying to communicate that, for example, with additive manufacturing. The idea of putting a machine in a hangar and putting a data set into the machine and thinking you're going to get a good product or remanufacture is not appropriate. So 605 tells us we need to substantiate new methods, and that's been an important requirement for us. And it's test and analysis. I'm going to link the discussion on CSs across to another really important requirement, which is damage tolerance and fatigue. This is the backbone to requirements. It again links us to the basic regulation. It says we need to be good for fatigue. It says at the moment corrosion and also accidental damage. And here's an example of us trying to manage with minimal pain the requirements. It says corrosion. That just reflects a technology set when the rules were written. That's a very metal-centric world. So that's being changed across to environmental damage to catch the new technologies and the composite materials in particular. We need to catch accidental damage. This is a driver for composite materials. The emphasis has changed in this requirement, and we're emphasising that through guidance and support documentation, and that's both production and in service. And we've already got in the requirements the provision. It says you need to inspect to ensure that you find these damages, you repair them before you've challenged your residual strength reference points. And it's fairly clear. It doesn't even say visual inspection, it says inspection. Even better for the new technology evolution, it says other procedures. There's nothing that, it doesn't even have to be an inspection. So we already have provision in place here at the regulatory level to accept process control rather than inspection control, to accept structural health monitoring into the process. So we have a framework to work on that exists already. And just a little reminder of that bottom note, we don't actually require we don't actually certify materials or inspections. They all get accepted as part of the process with the product. So how are we actually actively managing this situation internally at the moment with change? Well, we set up a strategy, a technology strategy, and it's got some fairly basic elements in there that you'd expect from any particular strategy. You need to understand the technology. You need to identify the environment and other risks, environmental risks. I say environmental, I'm thinking composites there. And you need to define and implement the mitigating risks. You need to monitor and evolve that, what you're managing, and you need to review and revise on a regular basis. And we already have that. In terms of composites, we have a draft developing composite strategy. We're obviously, well, I will talk about it in a minute. We have an additive manufacturing strategy. We've set up a national airworthiness authority materials network to start to generate a harmonised activity across Europe with these new technologies, reference to materials. Part of that includes a working group, which, as you see, Matt is the engine guy. I'm chairing it. We've identified across all disciplines within EASA focal points. I've deliberately put this slide up with names and contact details so that you have direct access to the people who matter in this network or this group we have within EASA. We also have a risk and mitigation matrix. This looks at the issues that, well, what do we already have in place which might help us manage this? I've already pointed at the existing requirements, which are pretty robust at the requirement level, maybe not the guidance level, but certainly the requirement level. Then when we identify gaps, we need to identify how we create the new mitigating factors as we progress with this technology. We're also using other tools. We're using the certification memos, which you may well be familiar with. This is a tool for us to communicate with industry and clarify points. And we've been using this to tie an early relationship with the manufacturers. As I've mentioned before, this is moving so quickly, this technology now, that we don't have the freedom we had in the past with evolving technologies, where there were enough people with enough experience to transfer between the regulator and industry on an occasional basis. So we have to find a way to catch up. And what we've done is implement a process where we're asking industry to talk to us about their production, their design activities, and engage with us at the appropriate point. We want to do a minimum pain approach. We want to work in a way that we fit in with existing audit schedules. As you tell us this new technology is arriving, tell us about it, and we will involve the appropriate people as we go along. In addition to that, we have started more intense or proper workshops. We had one last month at EASA, specifically on additive manufacturing. And we have regular communication with the other regulators, such as FAA. So we have a reasonable strategy in place. I think the evidence is that it's starting to work, and certainly working with the organisations we've had here just talking to us earlier. And with that, I'll hand back to Matt.
Yeah. So just picking up, and Simon, if you could move on. Thank you. So just picking up and highlighting on two of the points that Simon made on the last slide. So with the new implementation of new technologies, one of the key issues for EASA is engagement between the players in the technologies and between the agency and the applicants. And one of the tools we've used to do that is the construction of a certification memoranda. It's gone through the first draft stage, and it is now in the comment response period. That document tries to set out the EASA position on the policy regarding additive manufacture. It is really a starting point for us for opening discussion and communications with the applicants. We've tried to fulfill a performance-based approach, and it starts from the point, as Simon has described, that the base requirements are probably sufficient. But as we move forward, there could be room for additional policy as the technology develops. But one of the key messages for us in that cert memo is to encourage applicants to engage with the agency, to highlight the importance of interaction between the design organisation and the manufacturing organisation in these very key process-driven situations. But also to encourage applicants that they should also engage with their national authority in the manufacturing context. And at a technical level, where it focuses on is trying to get detail, not detail, but trying to lead in the direction of process control and material qualification. And we're asking applicants to work with us, take us with you on the journey as you establish the relevant process control and material qualification requirements. And the second tool that we've used to engage with everybody is, as Simon said, the additive workshop. In September, we had the first of a series of additive manufacturing workshops that was hosted by EASA in Cologne. That was attended by a range of people from industry, some of which are here with us today, but we saw applicants across the product spectrum that we see in EASA. We had machinery manufacturers there, we had research institutes, we had a range of authorities within Europe, and we had the US regulator, the FAA, as well there. It really was a venue to engage and foster interaction between the relevant participants. Some key messages came out of that, as you can see on the screen, and these were, how do I put it, understanding your design space, understanding the flaws that are possible, either eliminate those flaws or build those into your assumptions when you set your design criteria. So in the engine world, we consider that in terms of, as engine manufacturers will be familiar, the concept of the engineering plan and the manufacturing plan. The engineering plan sets out your attributes that you required and the assumptions that you make, and the manufacturing plan then comes along with the, how do I deliver a product which meets those assumptions and those attributes? And that's the closed loop approach we see in these process-driven manufacturing techniques as we've tried to describe. And that was one of the key messages that came out of it, was understanding the process, understanding what it's capable of, and building that into your design assumptions. I think lastly, to steal one of Neil's comments, the intelligent user, the intelligent customer. we in EASA consider that goes equally for us. We need to be an intelligent regulator, an enabler, and to work with the industry as these processes and these techniques develop. And therefore, training is relevant for everyone. Training is a key to this. It's a step-up game changer for some people, and that goes for us too. So.
Not quite done. So, just concluding, a quick reminder, which I should have really put at the beginning, when we implement changes of any type, we're looking for this equivalence. And what does that mean? It means that we're trying to make sure that these changes don't reduce the acceptable level of safety that we have at the moment. So that's important. The opportunities provided by these new technologies is forcing us to engage more closely with industry very quickly and at the right point of maturity in terms of the relationship to certification and integration into service. We think the regulatory backbone is okay. We think there's scope for guidance development. That'll depend on criticality of application. It'll depend on basically resource priority, and we'll be kind of linked to other industry drivers. We're using, for example, the standardization bodies much more extensively, like SAE, than we did before. There's a logic that the items that will mature first will be the priorities that industry identifies through the standardization bodies. Of course, that means very specific, unique processes to any particular company have to be managed. We still have to meet those objectives, safety objectives. But where industry is telling us a clear message, whether it's at the moment it's laser beam, and we have NADCAP developing a pretty good checklist, for example. We recognise that. We're going to use that whenever we can to try and reduce the pain in terms of our engagement, which I think is in line with earlier discussions today. And not forgetting R&D, we're going to try and engage properly. We're developing a better relationship recently with the Commission, and perhaps build on Clean Sky activities. And training is one item that just keeps coming through, and I think we're going to be talking about that in a minute, judging by the questions we're getting. And I think anyone who was at the additive manufacturing workshop, or indeed the composite workshops in the last few months, will be understanding that. So with that in mind, I mean, we're trying to work with industry in a way that means we can address these new integrated technologies in an appropriate and safe way. So with that, I think we're going to be following the questions.
Thank you, Simon. So, Simon, while you're still there on the podium, one of the questions that has come up and is quite thank you, has shown interest with the audience as well as, what is the role of the regulator in research and development in such fast-moving technology implementations? Where do we sit, and how can we participate in that?
It's quite an interesting question. I mean, as a regulator, we're interested really, I mean, blue skies research is of interest to us for the long distant future, but as the reality of a regulator, we've got to pick up the maturing technologies. And this is something which, back to the link with the Commission, we're trying to work on, because again, it'll be industry partly driving the subject areas. So we're saying to you, industry, engage us at the right point to optimise the benefits in terms of the certification path. We think there's some benefits to be gained. We've already seen it to some extent. Well, with the LEAP engine, we kind of engaged pretty quickly on the new technologies there, whether it was the fan blade or the nozzle or the retention structures on the nacelles. They're all new technologies, but that pays off, pays premium for industry to do that. But so, summarising, R&D is important, but really it has to be maturing our R&D, or we could waste a lot of time heading into dead ends.
Thank you, Simon. Okay, so you can all see as well the questions that the audience have posed. Just taking a look at one of those there. So if I could pose this question to Jose. with the advanced processes that we see and going through here, do you feel as a manufacturer that that requires a higher skill set in the production environment than the traditional processes, if I may?
I think that is part of our company to improve the skill of all the people. But obviously, yes, we are improving the skill of the people, and not only a skill. Sometimes it's a question of mentality. I have the feeling that very often when we are speaking about the process control specimen, etc., more than a technical item is a mentality problem. Some people are very happy to keep the today status, and very often it's as I said, it's a question of mentality and to try to rethink what we are doing today. Okay.
Thank you.
So, training questions. One of the training questions here is about what are we doing with the, was that the maintenance world? Yeah. For training. Well, I mentioned it a little bit earlier. We were the workshops that have been on recently on composite materials. There's been a lot of discussion about this. We're trying to encourage certain levels of training. We've identified certain levels of knowledge associated with certification activities, whether it's being production, design, maintenance, and we're working to push that forward. There are a number of harmonised activities going on where we might be able to come up with something more formal. Part 66 is under review and revision. That may include an appendix or a guidance in terms of training expectations and knowledge base. At the moment, it's a very high level, but it needs to step forward. We need to improve that. As I said earlier, we have the new technologies step change in terms of composites in large airframes. That's suddenly a very large population of maintenance people exposed to composites instantly. We need to have some level of guidance or expectation, even in a performance-based regulatory system. We should be given a clue or an indication of what we're really looking for. And so we are working on that training. In terms of additive manufacturing, that's just moving so quickly that, you know, if you look at the standardization bodies, they need, and some of the other activities that are going on out there, there's activity to try and find people who can actually be auditors. But there aren't even enough people out there to be auditors at the moment, so it is happening very rapidly. So it becomes internal control. So for standardization bodies and other guidance systems for audit guidance, there's going to be a need to find these people quickly and get them moving very quickly. And that needs some kind of training strategy, which I think the manufacturers are going to have to engage with. Yeah.
Jan, one of the favourite questions, and we've already touched on it, is related to drones. I think, to be fair, you've explored that with us, but do you have anything further to say on that matter?
So did we tested the engines on impact of the drone? The short answer, not to my knowledge. The LEAP engines has been tested through an extensive test plan, which include drastic weather conditions like icing, water, hailstorms, as well as multiple bird injections with many sizes in order to prevent from any catastrophic event. The question of the drones maybe I think is a bigger picture than only the engine. There's some challenges on the drone questions, on the how to work with the authorization of flights, the capacity to work on the air traffic. We spoke this morning, for example, with the space between airplanes, that kind of thing. I think drones requires work on the full picture.
Thank you very much. Sorry to put you on the spot there as well. So, one last question, I think, unless, is there anything anybody would like to raise from the audience at this stage? Okay, thank you. Okay, so we'll pick one last question from the list here. I think if I look at the question there, Simon, the plan to establish qualification criteria and training requirements of maintenance staff, I think it's fair that that's not something we're directly engaged in at the moment, but we have a member of the team, certainly in the additive realm, who is that's how we've set up the team to look at the threats, to look at the risk matrix with new technologies. Do you have any thoughts?
Yeah, and further to what I was saying about training earlier, there is a difficult area about what training means, a qualification. We're very careful about that because there's pressure for transportable qualification, and I think there's a lot of value in building block qualification, which coupled with product functions at a safe level, but I think we need to address that. It's in discussion as a harmonisation issue, the need for qualification. So I can't give you an answer to that at the moment, but I've given you my opinion because I think a qualification as a building block towards something else with on-the-job training and type course activities which are standardised perhaps through OSD, that kind of activity, that gets us somewhere more consistent and useful in the future.
Thank you, and with that, thank you very much, Simon, and thank you to my panellists. And with that, we'd like to draw this panel to a close. Thank you.
Thank you very much. It's time for the next coffee break. How about we shorten the coffee break and we come back here at past so that we finish the day a little bit earlier. Is that okay? What did you say, Jean-Marc? Transparency, democracy? So 3:30 back here. Thank you.